Hi everybody, this is going through Level 3 2022 Physics Mechanics paper, and the aim of this is to help you check the paper once you work through it yourself. Now, one of the important things you need to take care when you're doing the external exam is don't write in on any crossed or hatched area. That's the center of the page because that's going to be cut off when the booklet is marked. Okay, let's get on with the paper now. The first question's on rotational motion. Some children are playing on a roundabout. Riley pushes the roundabout and gets it spinning at a constant angular speed. It makes one revolution in 1.23 seconds. Now that's going to tell you that's the period. Okay, what do we have to do? Show that the angular velocity is 5.11 rads per second. So in any show that question, you must write the formula, substitute, and give an unrounded answer and then round it. So here's the answer. This was an achieved question. Okay, don't forget the unit. It's radians per second. The next one, Riley stops pushing and 30 seconds later, now this 30 seconds is the time, the roundabout has slowed so that it takes 2.04 seconds to make one revolution. So the time to make one revolution is the period. So there are two times there, but you just need to recognize which one's the period and which one's the time. The roundabout can be approximated to a spinning disk with a rotational inertia of 57.6 kilogram meter squared. I is the rotational inertia. Note what I've done. I've highlighted the numbers and I've put a letter next to it. Okay, determine the average angular deceleration, so that's your symbol, of the roundabout as it slows. And the second thing, calculate the average frictional torque acting on the roundabout as it slows. So for this, you need to use the kinematic equations for rotational motion. So your initial angular velocity is 5.11 rads, which is the same as that. And in order to get the final angular velocity, you need that one. So omega f is 2 pi over t, and this is your t, and you get that much. And the time taken for the whole thing is 30 seconds. Now you use the equation, omega f is omega I plus alpha theta. So you substitute, and you get a negative answer because it's slowing down to a stop, and you get that as your answer. So if you've got this much, you get an achieved because you've only answered one part of the question. The second one is the frictional torque. So torque is I alpha. So in order to get the torque, here's the rotational inertia from there and what you've just calculated, the angular acceleration. So you multiply the two and you get the answer, and then you get your merit. So you need both this. However, for a question, you'll only be given one of these two. You can't get both these scores. Okay? Then, 4 friends all ride on a roundabout in the positions shown in the diagram. So these are the 4 people. Explain using physics principles what the friends can do to make the roundabout speed up while staying on the platform. Exclude all influences external to the platform. That means there's no external torque. Speeding up when someone's spinning means the angular velocity is increasing. Now all these people are standing towards the edge or the periphery of the roundabout. So how do we answer this question? So taking on from here, when you don't have any external torques, then angular momentum is conserved. So you need to make that statement, and if that's the only thing you've written, you probably get an achieved there. In order to increase angular velocity, remember we said that angular velocity might increase, the rotational inertia of the system needs to decrease, okay? Because angular momentum is conserved, and in order for the angular velocity to increase, the rotational inertia needs to come down because the product of these two should be the same. So this can be done by changing the mass distribution. So if you recognize that, that's probably a merit. Now, the friends, what can they do for this? The friends can move closer to the axis of rotation or to the center of the roundabout, thereby decreasing its rotational inertia and increasing the angular velocity. So if you said all this, you get an excellence. And remember, you only get one grade, but I'm just showing you how it's broken down. Now, Matilda wants to run and jump onto the initially stationary roundabout, holding on to poles at A or B. So that's B and that's A. In order to make it spin as fast as possible, and she tries different jumps onto the roundabout. So she tries one jump this way and she tries one jump that way. Now, in order to make it go as fast as possible, you want maximum torque. Okay, and you know that torque is force multiplied by distance, but this distance is the perpendicular distance. So, assuming that she always jumps at the same speed, explain which jump, A or B, will make the roundabout go faster. So here we go. Force times radius or force times perpendicular distance. So assuming she exerts the same force, the jump that produces the greatest torque will result in the roundabout going faster. So if you've said that much, you get an achieved. Now, since torque is F times R, jump A will produce the greatest torque as R, which is the perpendicular distance between the direction of velocity and the axis of rotation, is a maximum at A. So I've kind of annotated the diagram. Okay, so this distance is much greater than that distance there. Okay, and that's a merit if you said both those. Moving on. Now, Matilda, this is the same question. So it's parts 1 and 2. So it's only one final grade for all those two parts together. Now, she subsequently lets go of the pole and slips off the roundabout. Discuss the possible effects on the speed of the roundabout and assume there's negligible friction. So if there's negligible friction, there's no external force. Now, because of no external force, what happens is momentum is conserved. So the speed of the roundabout remains unchanged. And what happens is Matilda just carries her momentum with her. So it'll just keep going the same speed. So if you got all these parts correct, part 1 and part 2, and you got everything right, it's excellence. If you made one error, that probably merit. And if you had one thing right, that's an achieved. Now moving on to question 2, collisions in space. So comets and asteroids are loosely formed objects that are easily broken up, especially when they collide. In this scenario, this is 100 kilogram object moving with a velocity of 500 meters per second collides with the stationary 300 kilogram object, and I just call them M1, M2, V1 and V2. Okay, this is your 100 kilogram, this is your 300 kilogram. And what do we have to do? Calculate the distance of the center of mass of the 300 kilogram of the system from the 300 kilogram object when the objects are 4,000 meters apart. So this whole thing is 4,000 meters. Assuming this is the center of mass, all distances from the center of mass, so that is your x, and this is 4,000 minus x because the whole thing is 4,000. So using balanced torques, so you get 100 times this equals 300 times x, and then you solve for x and you get 1,000 meters. That's an achieved. Next one, calculate the gravitational force between the two objects when their centers of mass are 10 meters apart, and assume that the velocity of the masses are constant before the collision. So you use this formula, F is g, mm by r squared. So that's your g, that's one mass, that's the other mass, and square of the distance. And you get that as your answer, and that's an achieved. And then moving on, hence find the acceleration of the 100 kilogram objects at this separation to determine whether the assumption that the velocities are constant before the collision is valid. So F equals ma, or acceleration is F by m. So that's your force from this answer. Your mass is your 100 kilograms, and you get Same answer, but times 10 to the power of negative 10, which is tiny number. And because this value is so small, it does not have any appreciable effect on the velocity. Hence, the assumption that the velocities are constant is correct. Okay, so if you've said that, both those, calculated this and done this explanation, you get a merit. Okay, moving on. This is C. The objects collide with no external forces and form two rocks, A and B, and each of them have a mass of 200 kilograms. These move away from each other as shown in the diagram in directions at 20 degrees either side of the initial direction. So this is your initial direction. One moves this way, the other moves the other way. Now show that the size of the momentum of the rocks A and B are the same even though they're going in different directions, and use the space. So what I've done is drawn a vector diagram. So this is the velocity of A, velocity of B, because m times v is momentum. So this is an isosceles triangle since the masses are the same and each of them are at 20 degrees either side of the initial direction. Their momentum P equals m times B will be the same. Okay, then moving on. Calculate the speed of the rocks A and B, and you can use the space to draw vector diagrams, and begin your answer by calculating the total momentum before collision. So the total momentum before collision is m1v1 plus m2v2. Okay, so this is v1, that one was not moving. So your total momentum is 50,000 kilogram meters per second. The velocity of the center of mass, because that you need to know, moving on, is 50,000 divided by 400. Why 400? Because the total mass is 400, 300 plus 100. You get 125. And then if you just take, that's how I got the 125. So this is a vector diagram with velocities. So that's your 125. This is 20 degrees. That's the velocity of A. And so using cos, you get cos 20 is 125 by VA. Velocity of A is 133 meters per second. Now this goes all the way to excellence. So if you made one error or you used radians, then you get a merit. So this is your excellence answer. Moving on, pendulum on Mars. So if you see pendulum, that has to do with simple harmonic motion. Okay, some space explorers on Mars want to check that the electronic timers are functioning correctly, so they make a pendulum, and the mass of the rock that they use is 2.30 kilograms. So this is your mass. The distance from the center of mass of the rock to the fixed point is 1.83 meters. So that's your length. And this is Mars, so you can't use 9.81. The gravitational field strength is 3.72. Show that the time period of the pendulum is 4.41 seconds. Remember, always for show that, you need the formula and the unrounded answer. So use the formula. 2 pi is 2 pi square root of L over G. So it's square root L and square root G. So put that in your calculator, you get this. That's an achieved. Now they set the pendulum oscillating by releasing the bob 0.300 meters away. That means that's your amplitude from its rest. And at the same moment, they start the timer. So they're starting the timer at the end position. So what do we have to do? Determine the position, so that's your Y, of the pendulum bob from its release point 2 seconds after it's been released, and you can use the space above to draw a phasor diagram. So this is where they release it from, and how do I know if it goes beyond halfway? Because the total time taken from one end to the other and back is 4.41 seconds. So to go from one end to the other end, it takes about 2.2 seconds. So, and it takes a little over 1 second to go from there to the center. So it's actually gone from A to this point here. So drawing the phasor started from A, and this is where it went. So that's the whole angle it does. Now you can do this using radians or degrees, but stick to one. So what I've done is using degrees. This is one method. In 4.41 seconds, it does 360 degrees. Why? Because that's a period and that's the time it takes to do a whole circle. So in 2 seconds, how much does it do? Using proportion, it does 163 degrees. That means from here to here is 163 degrees. What am I trying to find out? I want to find this distance, and to this distance I can add 0.300 meters. So in order to find this distance, I'm using this triangle here. So if this much is 163, then this bit is 180 minus 163, which is 17 degrees. So this angle theta is 17. So if I know theta and I know this is 0.300 meters because that's the amplitude, it's very easy to find y. So that's going to be cos, isn't it? So cos 17 is y over 0.3, and I get y is 0.287, but they want the distance from here, so you add the 0.3 as well, and you get so much. So there's your achieved, merit, and excellence parts. Okay. Then the amplitude of the pendulum decreases from 0.300 meters to 0.2. Explain why the period stays the same even though the amplitude decreases. So the formula for the period is t is equal to 2 pi L over g. So it's independent or does not depend on amplitude. The only time the period will change is when the length of the pendulum changes. So you could say that. There's also another way of saying it. So just this much will do for your merit, because if you state that, that's your achieved, and the reasoning is your merit. Also, for simple harmonic motion, acceleration is proportional to displacement. So when the amplitude decreases, the acceleration will also decrease. But what stays the same is the angular velocity stays the same. And angular velocity is 2 pi over t. So if angular velocity stays the same, 2 pi is a constant, so t has to be the same. Okay, so that's another way to say it. Then what's to calculate the total energy lost when the amplitude decreases? Because amplitude is an indication of energy. So in order to calculate the energy, we need to first calculate the maximum velocity. It's kinetic energy, right? So the maximum velocity at any point is a omega. So you get the maximum velocity when the amplitude is 0.300 meters, and then the maximum velocity when the amplitude is so much. So the change in energy is change in the kinetic energy. So it's half times m. So those is constant, minus v1 squared times v1 squared minus v2 squared, and you get that's the energy lost, and that was merit. And that's the paper all done. I hope that helped.